Welcome back everyone. In this lecture we will see the definition of change of basis. So, as I said before, we want to understand how the matrix representation of some linear operator looks like with respect to two different bases. So, for which we need to understand the definition of change of basis of from one basis to another basis. Okay, so this is indeed recorded in some matrix. So, that matrix called the change of basis matrix. So, for which let us recall the notation that was used earlier. So, T is a linear transformation from V to V, and let us assume the dimension of V is n. So, we have a basis V1 etc. Vn, and we want to change this basis to B dash, we call it V1 dash etc. Vn dash. So, now we want to relate the matrix of T with respect to B and the matrix of T with respect to B dash. So, in order to do that, let us try to understand how one can relate the coordinates first. So, we take this Vj dash and we want to write in terms of the world basis. So, let us write it as some C1j V1 plus etc. plus Cnj Vn. So, these coordinates Cij, so that is recorded in a matrix, that is what called change of basis matrix from P dash to B. So, we define this P B dash to B. So, this is a matrix which records this coordinate change. So, this is called the change of basis matrix from B dash to B. So, if you think about it, the jth column is the coordinate vector of Vj dash in the world basis B. Okay. So, basically this is a matrix whose columns are given by the coordinates of this V1 dash, V2 dash and so on with respect to the world basis B. So, now what is the use of this change of basis? So, this is actually indeed records, so how the coordinates are related. So, let us try to understand how the coordinates of given vector related with respect to these bases. So, for which let us try to write down. So, start with the vector V in capital V. So, then we can write this V in terms of the new basis. So, write it as B1 V1 dash plus etc. plus Bn Vn dash. So, now what we can do, we can simply change this Vj dash using this expression. So, then this actually becomes summation Bj summation Cij, arrange from 1 to n Va. So, that means the coordinates of V with respect to this world basis Vi. So, that is given by this matrix P times the coordinate vector of V with respect to B dash. So, indeed, so the coefficient of Vi is given by summation Bj Cij So, that means the coordinates of B dash, the coordinates of V with respect to B dash times this change of basis matrix from B dash to B. So, that is exactly equal to the coordinates of V with respect to B. Okay. So, that is what recorded in this equation. So, similarly one can actually do the other way. So, I will leave it as exercise. So, similarly one can get that the coordinates with respect to B dash, you can get it from by multiplying the change of basis matrix from B to B dash and the coordinate vector with respect to B. So, now using this we can actually make connections between the matrix representation of T with respect to B and B dash. So, let us just work it out. So, we want to compare. So, what do we want to do? So, we want to compare the matrix representation of B and the matrix representation of B dash. So, for which what we are going to do, we will compute the coordinate vectors of the image with respect to both bases. So, now if we start doing this for the image with respect to B dash, so then recall that this is given by taking the matrix representation of T with respect to B dash and multiplying with the coordinates of V with respect to B dash. So, now on the other hand we can write this coordinates in terms of the change of basis matrix. So, that means, so this vector coordinates given by the change of basis matrix times the coordinates of T V with respect to the B. So, this is known already. So, now we just combine all these things. Okay. So, if we combine these two, then what we get? So, we get the matrix representation of T with respect to B dash times the coordinate vector coordinates of V with respect to B dash will be equal to the change of matrix from B to B dash and the coordinates of T V with respect to B. So, now if you think about it, the coordinates of B, sorry, the coordinates of V with respect to B is given by the change of matrix from B dash to B and the coordinates of B dash. So, if we just substitute that and then rewrite, so we get here P B dash B T B V B. So, now for this coordinates of V with respect to B we use this. So, in particularly we get the matrix representation of T with respect to B dash times the coordinates of V with respect to B dash equal to the change of basis matrix from B to B dash times the matrix representation of T with respect to B times the change of basis the change of matrix from B dash to B times the coordinates of V with respect to B dash. And since this equation is true for all V in V, so that would imply that these matrices are same. The matrix representation of B dash is given by the multiplication of these three matrices. The change of basis matrix from B to B dash times the matrix representation of T with respect to B times the change of basis matrix from B dash to B. Okay. So, this is what we get. So, now it is a very simple exercise that using these two equations. So, equation 1 and then equation 2. So, using 1 and 2, so it is easy to prove that these two matrices are inverse of each other. So, if we take P B dash B, which is equal to the change of matrix from B dash to B inverse. Okay. I leave it you to check this. So, if you use this information in the equation that we have proved now, you can see that. So, these are nothing but inverses of each other. So, that means the matrix representation of T with respect to two bases, they are similar. The similarity is obtained by this change of basis matrix. So, basically the matrix of T with respect to B dash is equal to P inverse times the matrix representation of T with respect to B times P, where P is nothing but the change of basis matrix from B dash to B. Okay. So, that implies that these two are similar. So, the matrices T B and the matrices T B dash, they are similar. Okay, this is something very important. It will be used in the course lot. So, now once we have this information, this allows us to actually define determinant of a linear map and a trace of a linear map. So, given this linear map T from V to V, we define the determinant of T to be the determinant of the corresponding matrix representation of T with respect to some basis B. Now, note that if you change the basis, then these matrices are similar. So, that means the determinant will not actually change. So, indeed, so this quantity is independent of the choice of the basis. Similarly, we can define the trace of T defined to be the trace of this matrix representation of T with respect to some basis B. Again, similarly, this is independent of the basis because of what we proved before. Now, let us move on to direct sums. So, I will just recall some equivalent definition of direct sums of two subspaces. So, we are going to use mostly internal direct sums. So, but we all know that internal direct sums are isomorphic to external direct sums. So, we will just stick with one direct sum, which is internal direct sum. So, direct sums. So, we can easily take any finitely many subspaces, but for simplicity we will just stick with only two subspaces of V. So, we take W1 and W2 to be both are subspaces of V. So, then we want to say that V is direct sum of W1 and W2. So, that means, so any vector that can be written as in a unique expression. Okay, let me just define it here. So, the very first definition you can take it to be, so any vector V of V is written uniquely as V equal to W1 plus W2, where W1 comes from capital W1 and W2 comes from capital W2. So, this is, one can take it to be one of the definitions of direct sum. Traditionally, one defines as follows: V equal to W1 plus W2 and W1 intersection W2 to be 0. So, this is another definition of direct sum. The third definition one can actually write in terms of the dimensions. So, V equal to W1 plus W2 and the dimension of V is equal to dimension of W1 plus dimension of W2. So, all these statements are equivalent. So, now if you want to rewrite this little further using external direct product, so then we can say that the following map, so which is defined from the external direct product of W1 and W2 to V, given by the tuple W1 W2 goes to W1 plus W2, this is an isomorphism. Now, once we know that V is direct sum of W1 W2, so then we can take a basis of W1 and then basis of W2 and then put them together to get basis of V. So, if B1 is the basis of W1, B2 is a basis of W2, then from this you can get B1 union B2, which is a basis of W1 direct sum W2. This is something very standard, so I will leave it to you. So, as I said before, one can generalize this to any finitely many collection of subspaces of V. I will just leave it to you to think about it. So, we need this notion of inner product spaces, so which we will actually recall now. So, this is something very strong tools that can be used in the representation theory of finite groups. Okay. So, let us first define what is an inner product on V. So, an inner product, it is a map which is defined from V cross V to C. So, this is inner product if it satisfies the following conditions. The very first condition is the linearity in the first variable. So, you have linearity in the first variable. True for all C1, C2 in C and V1, V2, W in W, sorry, in V. Now, the second condition is the conjugate symmetry. So, if you take WV in a product which should be true, which is equal to the conjugate of V comma W. So, note that given Z A plus I B, which is a complex number, the conjugate of the complex number is defined to be A minus I B. Okay. So, now the third condition is the condition about the non-negativity of the inner product V comma V. So, the inner product V comma V should be always non-negative, and whenever the inner product is V comma V is 0, then we should have V is 0. So, an inner product, it is a map satisfying these three conditions, and there are some natural standard examples which comes from the standard inner product on Cn. So, you can take Cn and then you can define the standard inner product as follows. The inner product between A comma B to be the summation A I B I bar, I range from 1 to n, where A is given by the vector A1 etc. An and B is given by B1 etc. Bn. And it is easy exercise to verify that this is indeed an inner product. So, we will be actually working with a slightly different space. So, which is indeed a free vector space on a finite set. So, I do not want to get into the definition of free vector space and all, but I will just define what is the space. So, you start with the finite set X. So, then you consider all maps from X to C. So, this is the set of all maps F from X to C, and this space can be made into a vector space by defining pointwise addition and pointwise scalar multiplication. So, this is the set of all functions from X to C. So, this is the set of all functions from X to C. Now, we define this addition, the pointwise addition, which is defined to be f of x plus g of x for all x in C. So, this is the addition which is called pointwise addition. And we also have this pointwise scalar multiplication. Now, it is an easy exercise to verify that with respect to these operations, this C x, the set of all functions from x to C, becomes a vector space. So, now for each x in X, we can define this delta function concentrated on X. So, for each x in X, let us define this delta x, which is a map from X to C, which takes the values 1 if y equal to x, 0 otherwise. So, now it is an easy exercise to prove that the collection of this delta functions del x, x in X. So, this actually indeed form a basis of this vector space C x. Indeed, it is more than a basis, it is actually orthonormal basis with respect to the standard inner product that we define now. So, we can make C x into inner product space. So, by defining the inner product to be the summation f of x g of x bar x in X. So, you define this standard inner product on C x. So, with respect to this, C x becomes inner product space, and it is easy exercise to prove that this B x forms a orthonormal basis. So, orthonormal means it consisting of orthogonal vectors, orthogonal unit vectors. So, orthonormal means orthogonal plus unit vectors. So, orthogonal with respect to the inner product. So, you say two vectors orthogonal if the inner product between them is 0, and you say some subset is orthogonal if the inner product between any two distinct vectors are 0. And it is an easy exercise to prove that if S is subset of V and S does not contain 0 and S is orthogonal, then that would imply that S is linearly independent. So, using Gram-Smith process, you can always get a orthogonal basis of an inner product space, finite dimensional inner product space. So, it is a basic fact that there exists always an orthonormal basis for any finite dimensional inner product space. So, now once you fix an orthonormal basis, it is easy to write down the coordinates with respect to the orthonormal basis. So, that is the advantage of fixing orthonormal basis. So, if we have an orthonormal basis, let us call it E1 etc. En. So, this is orthonormal basis of V, then given any vector V in V. So, we can write V as summation the inner product V E I I range from 1 to n. So, that means the coordinates with respect to B is given by the inner products. So, one can actually define the norm. So, the norm of V is defined to be the inner product between V and V. So, then with respect to the norm and inner product, we have this Cauchy-Schwarz inequality. So, the Cauchy-Schwarz inequality says the absolute value of the inner product of two vectors is at most the product of the norms of those vectors. Now, we also have triangle inequality. So, the norm of addition of two vectors is at most the addition of the norms of those vectors. So, what is the advantage of working in inner product space? So, for example, let us say we are in two dimensional space. So, given a subspace, so there will be many subspaces which will be complement to this space. So, let us say W1 is given, V is given. So, what is a complement of W1? Complement of W1 is a subspace of V such that V equal to W1 direct sum W2. So, we say W2 is a complement of W1 if V equal to W1 direct sum W2. So, now given W1, you can always choose a complement by extending basis. For example, you can start with the basis of W1 and then extend that to basis of V. Then using that information you can actually form a complement of W1 in V. But there are like many choices for this complement. But if you think about it, if you are working with the inner product space, we can actually take a very unique choice which comes from the inner product, which is the complement, which is the orthogonal complement of W1. So, by taking the orthogonal complement, we make a unique choice for the complement. So, what does it mean? So, here is a fact which is easy to prove. So, given subspace W 1 of V, one can define this orthogonal complement of W 1. So, which is those vectors in V such that those vectors which are complement to all the vectors of W 1. So, the inner product between V comma W is 0 for all W in W. So, then this W 2 which is W 1 perp is a complement of W 1 in V, that is satisfies that V equal to W 1 direct sum W 1 perp, and it is easy to prove. So, to prove it is indeed direct sum, so we need to check two facts. One is W 1 intersection W 1 perp is 0, and the second fact is that W 1 sum W 1 perp is exactly V, and this is easy to prove because if V is in W 1 intersection W 1 perp, then that would imply that the inner product V V is 0, and that would imply that V is 0. Now, this is to prove that W 1 sum W 1 perp is indeed V. So, it is enough to prove that any vector can be written as sum of vectors from W 1 W 1 perp, that is the definition. So, given vector in V, so we need to find the sum W 1 plus W 2, where W 1 is coming from W 1 and W 2 is coming from W 1 perp. So, to make this choice of this W 1, what we can do, we can simply take the orthogonal projection of V on W 1. So, basically W 1 you take it to be the orthogonal projection of W of V on W 1. So, what does it mean? So, you have this W 1 here, and then the vector is somewhere here which is V. So, then there is this unique vector which is orthogonal to this W 1. So, that is what we call it, let us say V hat, which is W 1. So, how this W 1 is defined, which is V hat? So, you simply use one orthonormal basis of W 1 and then write down V hat in terms of that. So, take E 1 etcetera E m, which is the basis of W 1. So, then this V hat is given by take inner product V E I range from 1 to m, and I will leave it to check that this W 1 is indeed works, and W 2 obviously should be equal to V minus W 1. Okay. So, this means whenever you have a subspace of V, then we can make a unique choice for the complement, and this is very much used in representation theory. I will stop here. We will continue with diagonalization and so on in the next class. Thank you.